Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
I want to try something a little different to start us off today. It's an experiment, really.
Okay.
It might feel a little odd, but just, humor me for a minute.
I'm intrigued. What's the plan?
I want you, and I want everyone listening, whether you're in the car, on a treadmill, or maybe just washing dishes, to just stop.
Okay.
Just for a moment.
Yeah.
And I want you to try and find a moment of total, absolute silence.
All right. Let's try it.
Just listen. Maybe you can hear the hum of the refrigerator or traffic outside or even your own breathing. But try to tune all of that out.
Mm-hmm.
Try to find the stillness that's underneath all of that.
Okay.
It's hard, isn't it?
It is. It's actually impossible.
It is. And here's the really unsettling part. Even if I could snap my fingers and transport you into one of those anechoic chambers they have at NASA.
The super quiet rooms.
The ones that absorb 99.9% of all sound. And even if you held your breath and sat perfectly still, you would eventually start to hear something.
You hear a whooshing sound.
A whooshing, maybe a high-pitched whine. You'd definitely hear a rhythmic thumping.
You're hearing your own biology.
Exactly. You are not a quiet place. We think of ourselves as these solid, singular things. But inside of you right now, there's a roaring conversation happening.
Mm-hmm.
And I don't mean that metaphorically. I mean a literal, high-speed, high-volume exchange of data.
It's deafening, really. If we could somehow take the cellular activity happening in your body this very second and scale up the volume to a human level, it wouldn't sound like a library. Not at all.
What would it sound like?
It would sound like the trading floor of the New York Stock Exchange during a market crash.
Wow.
Or maybe a stadium during the Super Bowl. It's a cacophony.
Because we aren't talking about a few dozen voices here, are we? What is the number again? I always forget.
The latest estimate is around 37 trillion. Give or take a few billion, depending on your size.
37 trillion.
Yeah.
That number is so big it doesn't even register in my brain.
It's incomprehensible. It's just a word at that point.
And these 37 trillion cells aren't just floating around in some kind of jelly, minding their own business.
No, not at all. They are shouting at each other. They're whispering. They're sending text messages. They're broadcasting emergency alert.
They're even shaking hands.
They're literally shaking hands. And that's the fundamental reality of biology that we so often miss. We look at a diagram in a textbook and we see these static shapes. Here is the liver. Here is the heart.
Right. It all looks so neat and tidy.
But living biology is an information network. It's an internet of biological matter that honestly makes our digital internet look like a couple of tin cans connected by a string.
And that is exactly what we are getting into today. We're exploring this incredible hidden world based on a really dense, fascinating text called The Hidden Language of Cells.
Mm.
And I have to say, reading through this, it made me look at my own hand and feel a little bit distinct from it.
Mm.
Like, who is actually running the show here?
It raises some very valid questions about agency, for sure. But primarily, it's about the software that runs the hardware.
Right. So the mission for this whole exploration is to decode this coordination.
Yeah.
Because when you stop to think about it, the logistics are just a nightmare. How does a cell in your big toe know that you just stubbed it?
Or how does your stomach tell your brain to put down the fork because you've had enough pasta?
Or something even more complex.
Yeah.
How does an embryo know, okay, on the left side we build a hand, and on the right side we build another hand, not a foot?
Yeah.
If that message gets lost.
Then you don't get a viable organism. It's as simple as that. The stakes are, they're infinite. This hidden language is the mechanism of life.
From the very beginning.
From the moment of conception to the healing of a paper cut to the very thought forming in your brain as you process my voice right now, it is all cellular chatter.
So we're going to try and crack this code today. We're going to look at the vocabulary these cells use, the actual words. We're going to look at their listening devices, the ears.
And how they translate that noise into action.
And perhaps most importantly, we're going to look at what happens when the line goes dead.
Or worse, when the message gets completely garbled, because that's really where disease comes from.
Okay, so let's start at the very, very beginning, the vocabulary. The source text poses a pretty simple question that I have to admit I hadn't really considered before.
And what's that?
If I want to tell you to pass the salt, I use my mouth. I create sound waves. You hear them with your ears. Cells don't have mouths. They don't have vocal cords. So physically, how do they speak?
They use chemistry. And this is the first big mental shift we have to make to understand the source material.
Okay.
Human language is abstract. I say the word apple, and you imagine a red fruit. But the sound apple, the actual vibration in the air, isn't a fruit, it's a symbol.
Right. The word is just a pointer to the thing.
Exactly. But in the cellular world, the language is physical. The word is an object.
An object.
Yes, a three-dimensional molecule with a very, very specific shape. Imagine if, instead of texting you the word key, I literally threw a physical brass key at your head.
Okay, ow.
The object is the message. Its shape contains the information.
So a cell builds a physical thing, a molecule. That basically means grow or die or move over here and just, throws it out the door.
Essentially, yes.
Yeah.
These are what we call chemical messengers. And just like we have different ways of communicating, I could email you, I could whisper to you, I could put up a giant billboard on the highway.
Right. Different things for different jobs.
The body has different types of chemical mail.
The source text breaks these down into categories, and I really like the analogies here because it helps organize the chaos.
It does.
The first one is the broadcast system, hormones.
Hormones. These are the heavy hitters, the long-distance carriers.
The text calls them the radio broadcast or snail mail of the body. Why that specific distinction? What makes them slow?
It's because of how they travel. See, hormones are produced in very specific factories called endocrine glands, your pancreas, your adrenals, your thyroid, places like that. When they release a message, they don't send it to a specific address. They just dump it into the bloodstream.
The highway.
Exactly, the public highway. And once it's in the blood, that message goes everywhere. It's not a private note. It washes over the brain, the toes, the liver, the skin. It is a system-wide broadcast.
So if the pancreas releases insulin.
That's a classic example. Let's walk through it. You eat a bagel, your stomach breaks it down, glucose sugar enters your blood. Your blood sugar spikes.
Okay.
The pancreas has cells that can literally taste this sugar-rich blood, and they say, okay, time to work. They start printing out millions of these little insulin molecules. They dump them into the blood, and now that insulin is traveling to every single corner of your body shouting, there is sugar available, everybody eat it up.
And everyone hears it. Every cell.
Potentially everyone. Muscles, liver cells, fat cells, they all hear that broadcast. But, and this is the key to why it's snail mail, hormones are slow.
Slow. But I feel like things happen pretty fast when you eat.
Relatively speaking. I mean, think about how long it takes for your heart to pump blood all the way from your chest down to your feet. Seconds, sure. Maybe a minute to fully circulate.
Okay, yeah.
In the world of biology, where some things happen in microseconds, that is an eternity.
So you would never use a hormone to tell your hand to pull away from a hot stove?
God, no. You'd burn your hand off before the message even arrived. Hormones are for big global state changes.
Like what?
Growth, puberty, your overall stress response, digestion, things that take minutes, hours, or even years to unfold.
But adrenaline is a hormone, right? And that feels pretty much instant.
It feels instant because the effect is so dramatic. But compare it to a SOT. When you get scared, your adrenal glands dump adrenaline into your blood. It still takes a few seconds to really hit you.
Oh, okay.
Then your heart starts pounding, your lungs open up, your pupils dilate. It's a state change into fight or flight mode, but it's not a reflex. It's a system update.
Got it. Okay. So if hormones are the snail mail or the radio, what if you need to send a DM? A direct, instant text message.
Then you need the nervous system. You need neurotransmitters.
This is the brain stuff. Dopamine, serotonin.
This is the brain stuff. But just think about the physics of it for a second. In the hormone system, the sender and receiver can be feet apart. The pituitary gland in your brain talking to the ovaries or testes way down in your torso.
Right, a long trip.
In the nervous system, the sender and the receiver are, well, they're almost touching.
The synapse.
The synapse. It's this tiny, tiny gap. We're talking nanometers. So to get a message across, the first neuron shoots a highly concentrated spray of chemicals, dopamine, serotonin, glutamate, directly into the face of the second neuron.
It's aggressive.
It's intimate,
Yeah.
and it's incredibly fast, milliseconds, because the distance is so short. This is point-to-point communication. It's not a broadcast. It's a fiber optic cable.
That makes sense.
This is why you can think fast, why you have reflexes. You don't want the message, that car is braking suddenly, to take a leisurely detour through your liver.
Fair point. So we have the broadcast system with hormones and the direct line with neurotransmitters. But then there's this third category that the source spends a lot of time on, And honestly, it sounded like a war movie.
Cytokines.
Ah, yes. The cytokines, the language of war.
I usually hear about these when people talk about cytokine storms or, you know, getting the flu and feeling terrible.
Right. And that's exactly the right context. Think of cytokines as the emergency broadcast system, or maybe the walkie-talkies of the battlefield. These are primarily used by your immune system.
So this is soldiers talking to other soldiers.
Precisely. Imagine a white blood cell, a little sentry, a macrophage patrolling the deeper layers of your skin. It finds a cut. It finds bacteria entering the breach. It doesn't have a brain. It can't decide what to do in a conscious way. So it immediately releases a cloud of these cytokine molecules, things like interferons, interleukins.
And what does that signal say? What's the message?
It screams, "Enemy sighted! We have a breach! We need backup at coordinate X."
And other cells can track that signal. They can. It's a process called chemotaxis. Other immune cells can literally sniff out the concentration gradient of that signal. They follow the scent trail back to the wound.
That is absolutely incredible. So that redness, that puffiness I get when I have a cut or a splinter,
that is a very crowded room of soldiers shouting at each other with chemicals. That is inflammation. It's the fog of war, managed entirely by chemistry.
wow.
Without cytokines, your immune system would just be millions of blind, deaf soldiers wandering around aimlessly, hoping to bump into an invader.
I love that image. It makes a swollen finger feel a lot more heroic.
It is a battlefield, absolutely.
Okay, next up in the vocabulary lesson, growth factors. These sound pretty self-explanatory.
They are. The name is pretty good. Think of them as construction orders.
Blueprints.
That is a perfect analogy. These are the blueprints. They regulate cell division and survival. You have things like epidermal growth factor, which tells skin cells, hey, we have a gap here from a wound. We need to divide and fill it. Or you have bone morphogenetic proteins, BMPs, which literally tell the body where to build bone and where to sculpt cartilage.
So when I was just an embryo, these are the guys shouting, "Put a leg here. We need an arm over on this side."
Yes, they are the architects of your body plan. And they're still working right now, maintaining all your tissues. If you, say, damage your liver, hepatocyte growth factor surges to tell the remaining liver cells to regrow.
Now, this next one was totally new to me. Adhesion molecules. The source describes this as, well, as a handshake. But aren't cells just distinct blobs floating around?
They are distinct, but they need to form tissues. A liver isn't just a pile of loose cells, it's a solid, structured organ. Adhesion molecules are the most intimate form of communication. It's physical touch.
How does that work?
Cells have these proteins on their surface, like one group called cadherins, that literally grab onto the proteins of the cell next to them.
So they are actually holding hands.
They are holding hands, and this hand-holding conveys critical information. It tells the cell, I am attached, I am in the right place, I am part of a tissue, all is well.
What happens if they let go? Or if one cell loses its grip?
If a cell loses that hand-holding signal, it gets very nervous. It often thinks, I shouldn't be here, or I'm lost. In a healthy body, that cell might actually shut itself down.
It kills itself.
Yes, we call it anoikis, which is Greek for homelessness. It's homelessness-induced death.
That is surprisingly touching, pun intended.
It is. It's a powerful signal.
And finally, the source mentions metabolites. This is just trash talking, literally.
In a way. But one cell's trash is another cell's valuable data. Metabolites are the byproducts of doing work. Like if you run a factory, you produce smoke. If a cell does work, it produces things like lactate or adenosine.
Right, like the lactic acid burn you get after a really hard workout.
Exactly. But that lactate isn't just waste. It acts as a signal. It leaks out of the muscle and tells other tissues, hey, we're working really hard down here. We need you to adjust your metabolism to support us. It's a status update.
I'm busy. Send more energy.
Precisely. So from hormones to waste products, everything is information. The body is just awash in these chemical words.
It's a soup of information, a constant churning sea of data.
It really is.
But that leads to a huge problem. And the source makes a really big deal of this. If I'm a cell and I'm floating in this soup of billions of messages, insulin shouting, eat, adrenaline shouting run, growth factor shouting divide, how do I know which one is for me? How do I not go completely crazy?
That is the million-dollar question, because if every cell listened to every single message, you'd have chaos. Your toe cells would try to digest food. Your eye cells would try to pump blood.
It'd be a mess. So how do they filter it?
Specificity. And this brings us to the next part of the story, the ears of the cell, the receptors.
The lock and key. I remember this from high school biology.
the lock and key. But I want to be a little more precise here because the key analogy is a little too simple.
Okay.
Imagine the surface of a cell. It isn't smooth like a balloon. It is studded with thousands, maybe millions, of complex, twisted, three-dimensional structures. These are proteins called receptors.
They're like antennas.
They're like antennas, but with a very specific, custom-shaped dock at the tip, a shape that perfectly matches only one type of chemical messenger.
So an insulin receptor has a little pocket that is exactly the shape of an insulin molecule.
Exactly. And nothing else fits. If a molecule of adrenaline comes along and bumps into that insulin receptor, nothing happens. It just bounces off. It's the wrong shape.
It's like trying to put a Nissan key into a Ford ignition.
Perfect. That's exactly what it's like. So if a cell doesn't have a receptor for a certain chemical,
it's effectively deaf to that message.
Completely deaf. That is wild to think about, isn't it? You could have a cell that is literally drowning in a chemical signal, and if it doesn't have the hardware to hear it, it just ignores it completely.
That's how everything stays organized.
It's how the body specializes. A liver cell needs to listen to insulin, so it builds thousands of insulin receptors on its surface. But a neuron in your brain might need to listen to dopamine, so it studs itself with dopamine receptors. They are tuning into different stations on the radio.
The source mentions that these listening devices, these receptors, come in a couple of different flavors. Some are on the outside of the cell, which makes sense, but some are on the inside. How does that work?
Right. It all depends on the nature of the messenger molecule. Most messages, like insulin or adrenaline, are water-soluble. They can't pass through the fatty skin of the cell membrane.
It's like oil and water.
Exactly. They bounce off, so they have to knock on the door.
And the door is the receptor on the surface.
They have to bind to what we call cell surface receptors. And the most famous, and frankly the coolest one mentioned in the text, is the G-protein coupled receptor, the GPCR.
The text called them switchboard operators.
They are, but mechanically they are just fascinating. Picture a protein that threads back and forth through the cell membrane 7 times, like a tiny thread sewing the membrane together.
Okay, I'm picturing it.
When a signal molecule hits it on the outside, the whole structure twists. It physically changes shape.
It twists.
It's like a lever. You push the lever on the outside, and the bottom part of the protein on the inside of the cell kicks a little switch. It allows the information to cross the wall without the molecule ever having to enter.
That is just elegant engineering.
Yeah.
But then you have the VIPs, the intracellular receptors.
Yes. These are for the special molecules like steroid hormones, testosterone, estrogen, cortisol.
What's special about them?
These molecules are fat-soluble. They don't need a door. They can ghost right through the cell membrane like it's not even there.
They don't even knock.
They walk right in. They bypass the front desk and travel all the way to the nucleus, the command center, to find their receptors waiting for them inside. It's a very direct, very powerful form of communication because they often interact directly with the DNA itself.
There's one more detail in this section that I found really, really interesting. The dynamic listening. The source says cells aren't stuck with the ears they were born with.
This is a crucial concept. A cell isn't a static machine. It's smart. It adapts. If a cell is getting shouted at too much, say there is way too much insulin around for too long, the cell can decide to take some of its receptors down. It downregulates.
It just takes the doorbell off the wall.
Essentially, yes. It says, stop shouting at me, and it physically swallows its own receptors from the surface to reduce its sensitivity.
Wow.
And conversely, if a signal is very faint, it can build more receptors to try and catch every whisper. It upregulates. This is actually the basis of drug tolerance.
How so?
Well, take something like caffeine or opioids. If you constantly bombard the brain with an artificial stimulant, the brain tries to maintain balance. It says, this is too loud, and it starts removing the receptors for that drug.
But the next time you take the drug,
you have fewer ears to hear it, so you need a bigger dose to get the same effect. You're constantly chasing the dragon because your cells are actively trying to ignore you.
the conversation is dynamic. The listener actually changes based on what it hears. That explains so much about addiction and tolerance.
It does. It's homeostasis in action at a molecular level.
Okay, I want to pause here because we've reached a really critical juncture. We have the message, the chemical floating around. We have the ear, the receptor that has caught the message. The key has turned in the lock.
Correct.
But usually the chemical itself stays outside the cell, right? Like you said, insulin doesn't actually go inside. So how does the information get in? How do we get from a doorbell ringing on the porch to the lights turning on in the kitchen?
This is the black box of biology. This is the next stage. Signal transduction.
Transduction. That sounds like a physics term.
It's just a fancy word for converting one type of signal into another. Think of a microphone. It converts sound waves, physical vibrations, into an electrical signal. That's transduction. The cell has to convert a shape change on the outside into a chemical action on the inside.
The source text uses a domino analogy here, which I think is great.
It's the best way to visualize it. When the receptor on the outside changes shape, remember that lever twisting, it physically nudges a protein that's waiting just inside the cell.
Okay.
That protein wakes up, changes its own shape, and then it goes and hits another protein, which then hits another one. A cascade.
But why? Why play this complicated game of telephone? Why not just have the receptor do the job directly? Why involve 10 different guys in the middle?
Two big reasons. The first is regulation, and the second, and this is the big one, amplification.
The megaphone effect.
Yes, and this is genuinely mind-blowing when you run the numbers. Let's imagine one single molecule of adrenaline. Just one hits a receptor on a liver cell.
One molecule, incredibly tiny.
One single molecule. That receptor turns on. It activates a G protein inside, but it doesn't just activate one. It stays on for a little bit, so it bumps into and activates maybe 100 G proteins before it shuts off.
Okay, so 1 becomes 100.
Yeah.
100-fold increase already.
Now, each of those 100 G proteins activates an enzyme. And each one of those enzymes is a little factory that can churn out maybe 1,000-second messenger molecules.
So now we're at 100 times 1,000. That's 100,000 signals.
Exactly. And those 100,000 signals go on to activate even more enzymes. By the time you get to the end of the chain, which takes mere milliseconds, that one single adrenaline molecule on the outside has triggered the release of 100 million glucose molecules on the inside.
Wow. So it's basically a biological pyramid scheme.
It is the most effective and beneficial pyramid scheme in existence. It turns a whisper into a deafening shout. This is why you can react so explosively to a sudden fright. Your body is designed to take a tiny input and create a massive, overwhelming output.
But that sounds incredibly dangerous. If it can amplify that fast, how do you ever stop it? How do you prevent it from going out of control?
That's where the chain of command comes in. The other reason for the dominoes, you mentioned the alphabet soup earlier, the Ross-Raf-Ecke-Arc pathway.
It sounds like a bad law firm. Ross, Ref, Mech, and Erk.
It does, but think of them as levels of management in a company. The CEO tells the vice president, who tells the director, who tells the manager.
Why?
Because at every single step, you can say, wait. You can get a memo from another department.
It's a failsafe.
It's a series of checkpoints. Because this specific pathway, the ERK pathway, usually tells the cell to do something very serious. To divide. To make a copy of itself.
And you don't want to do that casually.
You absolutely do not. Unchecked cell division is the definition of cancer. So the cell requires multiple confirmations before it commits to something that big. Did RAS sign off? Did RAF sign off? If any step fails, or if a stop signal comes in from another pathway, the entire message gets vetoed.
So it's bureaucracy, but it's bureaucracy for the sake of survival.
Exactly. It might seem annoying and inefficient, but it keeps you alive.
We also need to talk about the town criers inside the cell. The source calls them second messengers. You mentioned them briefly in the amplification part.
These are cool. Sometimes you don't want a linear one-by-one domino chain. You want to flood the zone. You want to tell the whole cell something at once.
Okay.
So when a signal hits, the cell might open a gate that lets in a flood of calcium ions, or it might create a molecule called cyclic AMP inside itself.
Like pulling the fire alarm.
Yes, that's a perfect analogy.
Oh, yeah.
These small molecules rush everywhere instantly, spreading the news to the whole cell at once. Wake up! Action stations! Calcium is huge for this. It's how all your muscle cells know to contract right now in perfect unison.
But it's not always a straight line, is it?
Yeah.
The source talks about something called crosstalk.
This is where the real complexity and the real beauty comes in, because a cell isn't just getting one email at a time, it's getting thousands.
Right.
Imagine a cell is getting a growth signal from one side, but it's also getting a stress signal from the other side, and maybe a lack of oxygen signal from the back.
It's like being in a conference call where everyone is shouting conflicting advice.
And the signaling pathways, the domino chains, they actually talk to each other. The stress pathway might reach over and physically block one of the dominoes in the grow pathway. It says, hey, hold on a second, we are starving here. This is not the time to divide.
So the cell integrates all the information.
Yeah.
It thinks.
In a chemical sense, yes. It processes the sum total of all of its inputs to decide on a final single outcome. It is a biological logic gate.
So what is the outcome? We've had the signal, we've had the receptor, we've had the dominoes. What actually happens at the end of the line? What's the point of it all?
The response, the action. The source breaks this down into 3 timelines, which I think is a really helpful way to visualize it.
Okay.
First, you have the immediate response. We're talking milliseconds.
This is reflexes, like a muscle twitching.
Yes. This is all about opening doors. Ion channels in the cell membrane just pop open. No new proteins are made. We just change the shape of things that are already there. This is how a nerve fires or a muscle twitches. It's instant.
Okay, what's next?
Then you have the metabolic timeline. This takes minutes.
Changing the factory settings?
That's a great way to put it. You see a bear in the woods, adrenaline hits, your liver cells instantly start chopping up their stored sugar glycogen to feed your muscles for running.
Right.
It doesn't take days to get that energy. It takes minutes. The machinery's already there. You just have to turn it on.
And finally, the long game. Gene expression. This can take hours or even days.
This is the most profound part, I think. The signal can actually travel all the way into the library of your DNA and decide which books to read.
This blows my mind every single time. A chemical from outside the cell can change which genes are turned on or off inside.
Absolutely. The final domino in that chain, like that ERK protein we mentioned, often has a VIP past the nucleus. It walks right in. It finds the DNA, and it acts as something called a transcription factor.
A librarian.
A librarian. It finds the right shelf and says, okay, we need to build more muscle now. Open up the muscle genes, and while you're at it, close the fat storage genes.
But wait, DNA is packed incredibly tight, right? I remember reading it's like 2 meters of DNA stuffed into a microscopic nucleus. How does it find anything?
It is unbelievably dense. It's like a zipped file on a computer. So the first thing the transcription factor has to do is initiate chromatin remodeling.
What's that?
It literally calls in other molecular machines to unpack the DNA, to unspool it from the proteins it's wrapped around so that it can actually be read.
That is some heavy lifting.
It is. But this is how you become you. This is how a stem cell decides to become a neuron or a skin cell. It's all about which signals it received early on and which books in its library it decided to open as a result.
Speaking of scripts,
Yeah.
there's a much darker script the source mentions. Apoptosis, the suicide signal.
Oh, yes. This is one of the most important and counterintuitive concepts in all of biology.
Sounds terrible.
We tend to think that cells fight to stay alive at all costs, but actually cells are programmed to die, and they do it all the time.
So it's not a failure, it's a feature.
It's a critical feature. And it's not a violent death like getting smashed or poisoned. That's called necrosis. That causes rot and inflammation. Apoptosis is a tidy, organized, pre-planned shutdown.
How does it work?
The cell receives a signal either from itself because it's damaged or from a neighbor that says it's time to go.
And it just listens.
It listens. It activates a whole new set of genes. It starts packing up its machinery into neat little bags. It chops up its own DNA into harmless little pieces. It shrinks away and puts up a little flag that says, eat me, so a white blood cell can come along and recycle it.
No mess.
No mess, no fuss.
But why would a cell do that? Why would it agree to die?
To sculpt you. Think about when you were in the womb. Your hand started out as a little paddle. You had webbing between your fingers. How did you get distinct fingers?
The cells in the webbing. They died.
They received the apoptosis signal, they committed suicide, they sacrificed themselves to reveal the shape of your fingers. Death is a creative force in biology.
So death literally creates the shape of life.
Poetic and true. It's also a safety valve. If a cell's DNA gets too damaged, maybe from UV light or just a mistake during replication, it realizes, I am dangerous. I might become cancer.
That's how it is.
It triggers its own apoptosis program. It falls on its sword for the good of the organism.
That is incredibly noble for a tiny cell.
It is. It's the ultimate form of biological altruism. The individual cell dies so that the colony, which is you, can live.
Before we get to when things break down, let's zoom out for a second. We've been talking mostly about single cells, but the source text moves on to systemic coordination, the body-wide web.
Right. Because you aren't just a pile of cells, you're a system of systems. And there are 2 main systems that coordinate this communication on a massive scale, the nervous system and the immune system.
We touched on the nervous system, the synapses, but the source mentions something called long-term potentiation. That sounds pretty heavy.
It sounds technical, but it's actually beautiful. It's the cellular basis of memory and learning.
So how does a cell remember something?
It's all about the connection. If one neuron sends a signal to another neuron over and over and over again, say, while you are practicing guitar scales or learning a new language, the connection between them gets physically stronger. The receiving neuron literally builds more receptors. The sending neuron makes more neurotransmitters. The volume of that specific connection gets turned way up.
Cells that fire together wire together. I've heard that phrase.
That's exactly it. That is physically what a memory is. It's not some mystical thing. It's a communication pathway in your brain that has been reinforced through use.
And the immune system. It's not just chaos.
Oh, it's a complex and beautiful dance. You have cells whose only job is to find an enemy, tear off a little piece of it, we call that an antigen, and then run to a T cell, a general in the immune army, to show it, look what I found. Is this a bad guy?
An intelligence report.
Exactly. And that presentation triggers the release of all those cytokines we talked about, launching a highly specific and coordinated attack. It's incredibly sophisticated.
And keeping all of this in check is the idea of homeostasis. The source calls it the thermostat.
Feedback loops. This is critical. You can't just have signals shouting, go, go, go forever. You need a stop signal.
Can you give an example?
Take the thyroid gland. The brain tells the pituitary gland to tell the thyroid gland to make thyroid hormone. It's a chain of command.
Okay.
But when the thyroid makes enough hormone, that hormone travels back up to the brain and the pituitary and whispers, hey, we have enough. Stop asking.
Negative feedback.
Yes. It keeps everything in a stable, balanced range. It's the same thing with the pancreas. Glucose goes up, insulin brings it down. When the glucose level is down, the pancreas stops making insulin. If that feedback loop breaks, you either get hyperglycemia or a dangerous crash.
Now, we've talked a lot about all these internal signals, but the source has a really cool section on sensing the environment. Cells are spying on the outside world too, aren't they?
They have to. We are organisms living in a world. We have thermoreceptors in our skin. These are proteins that literally change their shape when they get hot or cold. That shape change sends a signal to your brain that says shiver or sweat.
And mechanoreceptors.
These are fascinating. In your inner ear, you have these tiny little hair cells. When a sound wave hits them, the hair physically bends.
Right.
That bending motion pulls open a little trap door in the cell, an ion channel. Ions rush in and boom, an electrical signal is sent to the brain saying, I just heard middle C.
So hearing is just a physical push getting translated into a chemical signal.
Correct. Same with touch, same with blood pressure. You have cells that are physically stretching in your arteries, and that stretching tells the brain pressure is too high.
And photoreceptors in the eye.
Proteins called opsins. They sit in the cells of your retina, and when a photon of light hits them, they physically change shape. It's all the same principle. Physical stimulus leads to a protein shape change, which leads to a chemical signal, which the brain interprets as sight or sound or touch.
It really drives home the point that we are just big, walking sensing machines.
We are sensory arrays walking around, constantly collecting data about the world and turning it into an internal chemical conversation.
But what happens when that conversation stops? Or what happens when someone in the conversation starts lying? This brings us to the dark side of it all, disease.
Yeah, the source text makes a very, very compelling argument here. Many, if not most, major diseases are fundamentally communication breakdowns.
Let's start with the big one. Cancer. We usually think of it as a tumor or a lump, an invader.
But really, you can frame it as an insurrection. It's a profound failure of social signaling, a cell that goes rogue.
How so? What communication breaks?
Well, normal cells respect the rules of the community. They listen to stop dividing signals from their neighbors. They listen to apoptosis signals if they're damaged. Cancer cells ignore them. They unplug their ears. They often have mutations in those fail-safe proteins we talked about, like RAS or RAF, that leave them permanently stuck in the on-end position. They are screaming go at themselves 24/7.
So they become deaf to any authority.
Yes. And they also start lying. The source mentions something called autocrine signaling. Cancer cells can hack the system to produce their own growth factors. So they talk to themselves, whispering, grow, 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 while ignoring the rest of the body that's shouting, stop.
And they lose the handshake, right? The adhesion molecules.
Exactly. That's the critical step for metastasis, for cancer spreading. Normal cells hold hands tightly with those coherent proteins. Cancer cells let go, they become slippery, they detach from the community and wander off into the blood or lymph to set up a new rogue colony somewhere else. It is a total breakdown of cellular citizenship.
What about something like diabetes? That's a communication issue too.
A classic one. And it comes in two flavors. Type 1 diabetes is a sender problem. The immune system mistakenly attacks and kills the beta cells in the pancreas. There is simply no one left to send the insulin message. The letter never gets written.
And type 2.
That is a receiver problem. The pancreas is working overtime, sending out tons of insulin, shouting loud and clear. But the cells of the body have become deaf.
They've downregulated their receptors.
Exactly. Because of chronic overstimulation from high sugar diets, they've pulled their receptors off the surface. The key is there, it's trying to get in the lock, but the door just won't open anymore.
This framing really changes how you look at medicine. It's not just fixing a broken part. It's fixing the conversation.
That is exactly what modern therapeutics is trying to do. We are becoming communication hackers.
Give us some examples of how we hack the system.
Well, the most common are blockers. Think about beta blockers for high blood pressure or heart conditions. They literally put a piece of gum in the lock of the adrenaline receptor on the heart. Adrenaline comes along, tries to bind, but it can't get in, so the heart stays calm.
Or what about Herceptin for breast cancer? I've heard that.
Yes, that's a brilliant example. Some breast cancers have way too many growth factor receptors on their surface, a protein called HR2. Herceptin is an antibody that just goes and covers those receptors up. It blinds the cancer cell so it can't see the growth signal anymore.
And replacement seems obvious, like injecting insulin. You're just manually adding the missing letter to the mailbag.
Correct. Hormone replacement therapy is the same idea. But the future is even wilder. We're moving into regenerative medicine, using stem cells, or even CRISPR gene editing.
How would that work?
We are trying to rewrite the instruction manual itself. If a cell has a broken receptor gene, a typo in the DNA, maybe we can go in and edit that typo to fix the conversation at its source.
That is pure science fiction stuff.
It's happening in labs right now. The future is arriving very quickly.
We're coming towards the end of our exploration here, but I want to touch on the evolution section. Because this whole complex language, this isn't just a human thing, is it?
No. And that's the humbling part. The source points out that bacteria do this. They have their own version of social networking called quorum sensing.
Bacteria talk to each other.
They do. A single bacterium on its own is quiet and harmless. But if they multiply and get a big crowd together, they start releasing chemicals that tell each other, hey, there are enough of us now, we have a quorum, let's attack. They coordinate their behavior based on population density.
So this language is ancient.
Billions of years old. The basic logic, a signal, a receptor, a response, is conserved from the humblest worm to the most brilliant human. We are running on very, very ancient software.
And it's not simple. The source emphasizes complexity theory. This isn't a straight line.
It's a network. It's nonlinear. It's why medicine is so hard. You pull one lever over here, you give a drug, and because of all that crosstalk we mentioned, something completely unexpected happens over here in the liver. It's a web, not a simple ladder.
Which is why they are now using organoids, little mini organs.
Yes, growing mini livers or mini brains in a dish. Because studying cells in isolation on a flat plastic plate doesn't show you the conversation. You need the community, the three-dimensional structure, to see the language in action.
Wow. Okay, let's try and wrap this all up. We've gone from the silence of a quiet room to the roaring cacophony of 37 trillion cells. We've seen the chemical keys, the protein locks, the domino cascades, and the libraries of DNA being opened and closed.
It really makes you look at your own body differently, doesn't it? You aren't just a solid object. You are a shimmering, dynamic, endless conversation. Every single second, trillions of decisions are being made without you ever knowing about it.
It leads to a final, slightly provocative thought the source hints at. If my growth is just hormones hitting receptors, and my stress is just adrenaline, and my happiness is just dopamine, and my memories are just strengthened synapses.
Where are you?
Exactly. Where's the ghost in the machine? Are we just incredibly complex chemical gears turning?
It's the ultimate philosophical question posed by modern biology. But consider this, to add another layer. We are now entering an era of synthetic biology.
What's that?
We are actively engineering cells to speak new artificial languages. We are building biological circuits inside yeast and bacteria, just like you'd build a computer chip.
If we can program cells.
If we can program cells like we program computers, we can potentially program life itself. We could cure diseases by simply rewriting the memo that gets passed around. But it also means we are taking direct, conscious control of the fundamental operating system of nature. And what does the future of humanity look like when we become the authors of that code?
That is a very heavy question to leave us with. But for now, I'm just going to sit here and try to appreciate the trillions of whispers that are keeping me alive.
As you should. It's an absolute masterpiece of coordination.
Thanks for joining us on this journey into the hidden language. Stay curious, everyone.